Hello, everyone. In this session, I'll be talking about our recent initiatives on Line as an infrastructure platform. Let me briefly introduce myself. So my name is Yoshihiro Saegusa. I joined NHN Japan in 2005, which is the former name of Line Corporation. And since then, I've been in the network and data center area and responsible for over 10 years. And currently, since June of last year, I started to develop private clouds. And now my main role is to solve infrastructure issue in Line as a platform. Today I'll be talking about infrastructure. Let me touch on the scope of Line's infrastructure. So in this picture, as you can see, our infrastructure spans from data center to the OS. Also database and storage. And these components are also managed and operated in our infrastructure organization. So in this section, since I have a background in network, and I'm in charge of infrastructure platform, I will be focusing on these areas in this presentation. So Line launched 7 years ago, and we faced many challenges along the way. And looking back, we see that the increase in scale was the common trigger for these issues. The number of users increased, the number of servers increased, and the number of engineers and dev centers increased as well. So let me explain the current scope of Line. User traffic is over 1 terabits per second. We have over 30,000 physical servers and over 2,000 engineers worldwide in 10 domestic and overseas dev centers. And this number continues to grow as we speak, and the scale has caused many issues. These challenges are in mainly 3 areas. We simply lacked capacity as we scaled. The previous architecture was no longer efficient. We weren't able to resolve our issues. And it became no longer efficient. And third is an increase in operational cost. So let's take a look into these more in detail. So the first issue is network infrastructure. So compared to user traffic, there's a lot more traffic within the data center used to communicate between servers. So my focus in designing the architecture was securing as much bandwidth as possible for server communication. And previously, one network pod contained 3,200 servers. And one server had an interface of 10 gigabytes. So that means one pod was 16,000 gigabytes per second. And we used a 2N redundant configuration. So we ran into the first problem we ran into was the network bottleneck. So we had 3,200 servers. The network capacity was 16,000 gigabytes. So if you have servers constantly using up 10 gigabytes, it results in network congestion and network bottleneck. The communication becomes unstable. To avoid this, we tried placing servers with a lot of traffic closer to each other in the network. But this reached its limitation as the number of servers grew. So the other problem was the 2N redundancy was not as cost-effective as we wanted it to be. So we had 16,000 gigabytes per second. We need an infrastructure with 32,000 gigabytes per second. If we start scared with N, the cost performance goes down. So we had the problem of network bottleneck, and the 2N redundancy cost effectiveness were our two main issues. Next problem was connections. LINE's MAU in 4 main service countries, Japan, Taiwan, Thailand, and Indonesia, exceeds 165 million users MAU. The daily active user rate is 77% or over. So LINE infrastructure holds close to 50 million concurrent connections. And with these TCP connections, goes to the load balancer and is distributed to the LINE messaging gateway. So since the same TCP connection must be distributed to the same gateway server, the load balancer holds session tables for each TCP connections. Managing the session table was the most important part in managing load balancer, because the session table is the size of the session table is dependent on the memory size of the load balancer, because there's a limited number of memory size. So there's a limited size of the session table as well. So when the session table is full, communication fails, and for some users, they will experience network failure. To avoid this, LINE has several load balancers to ensure sufficient capacity. In terms, we also adopt a DSR configuration for our load balancers. So what it does, so traffic going from client to server goes through the load balancer, but the other way around, it does not go through the load balancer. The reason we do this is because client to server communication is generally less compared to the other way around. So we have the benefit of calculating a load balancer capacity based on the smaller traffic. But there is a drawback to this. The drawback is that we cannot perform granular control on session tables. So, for instance, if there's a system fails at a telecom company with many LINE users, or there's an issue with the LINE infrastructure itself, the LINE client sends frequent retry communications. So each of these communications will come onto the session table for each load balancer, and the session table will overflow. So this is the drawback of having this system. Scaling the session table was also an important challenge, and improving the bad cost effectiveness of 2N redundancy were the two main challenges. So the other main issue was the increase in engineers and dev centers. So LINE infrastructure team, LINE has a dedicated team for each layer of its infrastructure. So when an engineer wants to deploy the app to the production environment, we need to request an infrastructure team to each infrastructure team to allocate appropriate resources. Of course, when we had few engineers with less dev centers, we were able to manage this. But today we have more than 22,000 engineers. And it's not realistic to expect all the engineers to understand the infrastructure layers and submit accurate regex. It is unrealistic to expect all engineers to understand this. Of course, there's the cost of training these engineers to understand it as well. And of course, we'll receive requests from 2,000 engineers. The workload also increases for the infrastructure engineering side as well. So we needed to decrease the burden on both sides. So I've explained the challenges. Now I would explain how we resolved it. Before I explain how we fix it, let me share you our basic principles. Number one is solve the problem at its root. So we believe that fixing something only on the surface will only delay the issue. We need to resolve the problem at the architecture level. Number two, reduce operational burden. So even if we might have a massive capacity infrastructure that is most cost-effective, if it takes more effort to operate it or if it's cumbersome to operate it, I wouldn't want to actively adopt it. So we need to find fundamental solutions and lessen the operational strain. These are our principles. So going back to our problem, I decided on 3 requirements. One, capacity was our headache, so we needed to provide extremely high capacity network. Number 2, instead of an inefficient 2N architecture, we wanted an N+1 architecture that is scalable. And number 3 is significantly reduce operation cost and burden. So we wanted to design a network with no bottlenecks. Even if all servers used up 10 gigabytes of traffic, it should, in theory, still not end up in a bottleneck. To achieve this, we needed to have fundamental changes in the architecture. The basic architecture, we also adopted case studies at another large-scale data center network architecture. It took the closed network approach. So a closed network has an N+1 architecture in all of its layers, and it is scalable. And we decided to adopt a Whitebox switch for the network devices as well. Why Whitebox? OS is Linux-based, and we can benefit from the managing switch configuration when managing the servers. Because we have methods to manage servers in a 10,000 level, so we thought we could adopt this mechanism. So we started to explore Whitebox switch closed networks. At line, we had to also figure out TOR switch and the network configuration. At line, we have a double TOR switch. Previously, we connected server and TOR using L2. The other option to connect it with L3 was the other option. The decisive difference between these two options is how easy it is to maintenance it. With L2 technology, we can't gracefully switch the TOR switch with L2 technology. There's always a packet loss when we switch. With L3 connections, it used the L3 routing technology. The TOR switch can be gracefully and seamlessly switched. And it's also very easy to maintenance, so that was one of the big benefits for us. So this is why we decided to explore the L3 option. So if we go with this pattern, we also needed to change the configuration on the server side. We don't want this to impact the application, so we worked with our developers and first tested it with our key applications. So we found that there were no problems, so we went with L3 and used a Whitebox and a closed network. So this is the actual configuration in one of our websites. So this is 7,200 servers for one pod. And even if each server has a connection of a traffic of over 10 gigabytes, it would not compose a network bottlenecks. And it consists of 948 Whitebox switch. So this is a good example that closed network can scale to this magnitude.
So as for the challenge with the load balancer, we try to solve it at the architecture level. So the basic architecture is L3, L4, and L7 multi-tier configuration. The layer 7 is the messaging gateway server. And at each layer, we have N+1 configuration that is scalable. That was the aim. And for L3, ECMP and Anycast, the routing technology was used, and we can distribute easily with N+1 configuration. But the challenge was L4. So if we have the stateful method, if there is one node failure or one node maintenance, in order to minimize the user impact, all L4 nodes have to have the same session information synchronized. Otherwise, there's going to be user impact. So all L4 nodes have to have all of the information. That means that since the session table size is finite, this is not realistic. Therefore, session table, where session table is managed in a stateful manner, we thought about a method where we can have stateful method without session management. So for one TCP flow in identification, we need source IP address, destination IP address, source port number, destination port number, and protocol number. These 5 data is necessary for TCP flow identification. So we calculate the hash using these 5 data, and then we identify the target server so that the same TCP connection can be routed to the same server. And all of the L4 nodes are behaving with the same hash algorithm so that when there is a node failure or maintenance, the user impact is minimized. The remaining challenge is the performance for one L4 node. So we need to provide massive performance. So performance required from L4 node is 7 million packets per second. So L4 node, in terms of cost and maintainability, it is deployed as a software on Linux server. Normal Linux kernel stack means that the 7 million packets per second is too large to realize. Therefore, for the high-speed processing of packets, we need to think about the method. And at that timing, on Linux kernel, XDP function was added. What XDP does is normal Linux kernel network stack. Before the packet goes to the stack, on the NIC driver level, there is fast processing of the packets directly. By using XDP, we can reach the target performance. So that's why we started to test XDP, and 7 million packets per second was achieved through the test. So software-based stateless load balancer was developed using XDP, and this load balancer was deployed in the production environment in August this year. And maybe you heard the session in Hall B in the morning today. In the Line Ads platform, that is also on this load balancer. Last challenge is the expansion of developers and development centers. So the user side usage cost, and there was also the burden on the infrastructure operator side. In order to minimize the costs, we added the infrastructure platform layer where we can do automation, so that for the developers, as a method where they don't have to be aware of the infrastructure, they can operate the infrastructure. So to put it short, this is Line infrastructure turned into private cloud. And this private cloud is developed under the internal product name called Verda. And Verda was introduced in this event last year. So if you'd like to know the details, please look at the slides and video from last year's event. So Verda creates the mechanism where developers don't have to be aware of the infrastructure. I would like to explain about how we do that. So there are multiple VMs deployed, and load balancers VIPs assigned to these VMs. So when we deploy multiple VMs, so those VMs, if they are on the same one failure domain, there's no point. So they have to be distributed over multiple failure domains. Conventionally, this operation, after receiving request, the operators looked at the request from the developers, and they would do this assignment. And through Verda, developers can do this operation, but that is still remaining as workload. So this is deployed as a logic. So developers do not have to worry about this, and they can secure the resources that they need through the scheduling logic of Verda. And it's the same for load balancer. So as long as the load balancers are distributed, the availability of the load balancer is raised. And this is not done with intention, but Verda does it automatically. And the setting of the network is the same. So conventional network configuration and new network configuration are different, of course, in their setting. So the users, so this is a network configuration because this is the old network infrastructure. That would be costly. So without any awareness, the VMs would be configured. So we don't want the users to be aware of the infrastructure more than necessary, but we also have the policy where the users have to have awareness when required. And this is when they want to publish their public IP in load balancer. So just by setting VIP on the public using public IP for the load balancer, it wouldn't be published externally. There has to be a request submitted, and after the approval flow, the service would be published. The reason why we do this is if the internal service is unintentionally published outside as an operational mistake, that is a problem. So we have this awareness embedded so that users are aware and they need to intentionally do certain things. So far, I talked about what we have done in our infrastructure team. When you hear this, it seems that we have been solving our issues very smoothly. But in reality, that was not the case, and it was a series of many struggles. The biggest struggle was to deal with the change necessary with solving issues. So the conventional method could not be maintained while solving the issue. So in order to reduce the operational burden for the network, in order to introduce the Whitebox switch, we had to change the operational way so that we changed to the method of managing the servers. And automation of the platform level infrastructure. This is not just scripting and automation partially, but we need to have consistent policies overall to rebuild the software system. So in each case, if we continue the initiatives from the past, it's not something that we could just achieve as an extension of past initiatives. It required many changes. And for those changes to be embedded, maybe one way is to do it one way, one directionally from top-down order, but that would invite some resistance. And we have faced such a situation in the past. So for such major change to be executed, we need to clarify the goal, and we have to have the agreement with from everyone, and we have to carry out the change one by one. And another issue is to do with the time. So for architecture level improvement to be conducted, we have to implement such change in accordance with the life cycle. Infrastructure involves hardware, so the life cycle is very long. At shortest, it is 3 years, and at the longest, in the data center, 10 or 15 years. Therefore, once we miss a timing for a change or improvement, the next timing would be far in the future. So not missing the timing is important. So from daily operation, if in order to implement new technology and approaches, we have to research such element technology, and we also have to develop and hire human resources, which cannot be done overnight. So in order not to miss the timing for solving issues, we have to always prepare such foundation for realization of improvement. That's what we learned through this kind of project. And lastly, I would like to talk about the initiatives we are carrying out at LINE at the moment. The first example is to do with the network. Most of the services in LINE, until now, we had single tenant on single network. Most of the services were provided that way. However, in today's session, as was mentioned, we are working on fintech technology, fintech business. Therefore, there are different requirements that were never seen before for the network. And to these requirements, every time we are building the network to meet such requirements. However, with this method, it takes time, and also it also eats a lot of the infrastructure engineers' resources. So on one infrastructure, to meet various requirements, such element technology is now being researched. So what we are focusing on is SRv6 technology. This technology is one of the source routing technologies. The characteristic is that IPv6 transfer mechanism is the only thing that is required. And also, source routing, such flexible path selection is possible. And also, we can add many functions to the network. with this protocol. And using SRv6 for network multi-tenancy and service chaining so that we can quickly respond to business needs. That is the initiative we are now carrying out. Next is the initiative to do with platform using Kubernetes. So at Line, in various products in the production environment, we are operating Kubernetes. However, currently each development team is managing their Kubernetes cluster. Therefore, the management overhead is high. In order to solve this, the managed Kubernetes is used. So to explain the architecture, the Kubernetes clusters to be used by users is connected and managed by Rancher, which is OSS. So users are not exposed to Rancher directly, but users' interface is on Gateway API that is developed by us from scratch. So the reason for this architecture is because we don't want to depend on a certain open source software, and also if Rancher has, for example, scalability issue, we can respond to it and solve it from the Gateway API. So the current status is that it is now in closed beta, and we are having developers to test this. Next year, maybe in springtime, we can deliver this in the production environment. And another platform where we're using Kubernetes is Event Handler. That is the project. So in this platform, we have infrastructure and application operations to be supported by this platform. So in your daily operation, if a certain event occurs, you have an action executed. For example, if you see a certain log, you send a notification. And another case is where you would conduct a test every hour. And this event handler, you have any event and any function connected to each other so that it is a function as a service. The function can be executed. So this is a function as a service where the function can be executed to an event. So the benefit is that in order to realize this, you would need webhook, and you would also need to build API server. But such work is not necessary. Moreover, the event and the action can be linked and managed as cloud resource so that such operation can be visualized. And this event handler is developed based on Knative, which was published from Google as open source software recently. So far, I have talked about our initiatives. Let me summarize. So the network challenges were solved from the root using closed network and multi-tier load balancer architecture. And we are using Verda in order to lessen the burden both on the developers and infrastructure users. There are still challenges to be solved, and we want to solve them fundamentally with the principle of reducing the operational burden. That is what we are working on, and I hope that I was able to convey that to you. Thank you very much.